Welcome to this lecture series in linear algebra. We are starting a new module which will be about bilinear forms. This will serve as a prerequisite or a precursor to the study of inner products. Although not completely essential, I think it is a very interesting topic in its own right. So let's get started. What we need to follow this lecture is mainly the identification between the vector space, identification between any given vector space and its double dual, and the various concepts associated around the notion of dual, like the notion of transpose, etc. So let us at least recall one thing. If V is a vector space, then for any vector V in the vector space, we have an element in the double dual defined as follows. Right, so this is the definition of this person, and the map capital phi going from V to the double dual of V, which takes little v to phi sub v, is an isomorphism. So let me stop at this as far as the recall goes. Here are some problems for practice. And now let us get started. So what is a bilinear form? Fix a vector space V. Let's say F is the base field. Then a bilinear form. A bilinear form on V is a map F from V cross V to the base field. Unfortunately, I'm using little f and capital F, but I do not want to change it. I hope there is no confusion. This little f has nothing to do with capital F at all. Alright, so it is a map from V cross V to F such that the map, so two things. This is linear for all V in V. Now you may question what is meant by this. I will explain, but let me finish the definition. And the second thing is, let me write a U here. U is better. Yeah, and F blank V is linear for all little v in the space capital V. Okay, so what is meant by this notation? So this is a map. When we write this thing, this is a map from V to F, which takes x to f of u comma x. That's the definition. And similarly, f blank v is the map from capital V to F, which takes, let me write maybe, x was a bad idea. Let me write y here. Here I will write x. So just a pretty notation. So the point is, what is a bilinear form? A bilinear form is a map from V cross V to the base field, such that if you freeze the first coordinate, you get a linear map, and if you freeze the second coordinate, you again get a linear map. And no matter what you freeze it with, that is irrelevant. You just pick a vector of your choice, you freeze that coordinate, you get a linear map. So that's the definition. One can note that f of a1x1 plus a2x2 comma v is a1f x1v plus a2 f x to v for all, for all what? So this is for all v, for all a1, a2 in the base field, and for all vectors x1 and x2. So that should be clear. And similarly for the other side. So here you fix a u and so you put a u here, and here you write a linear combination and so on. This is just an elaboration of this point, these 2 points, nothing more. Okay, so that's the definition of a bilinear form. It is unclear why such a thing is useful, but we will look at some examples and get comfortable with this. Before that, here is a notation. The set of all the bilinear forms on a vector space is denoted in this fashion: bil v, bil, and then a v. All right. So let's see some examples. So suppose this is our vector space, f is a field, then this is our, one of the most basic examples of a vector space. So one can define a bilinear form as follows. So this is defined as f of x comma y is equal to x1 y1 plus dot 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 x and yn, where by x here we mean this tuple x1 up to xn, and by y we mean this tuple. So each xi is a scalar and each yi is a scalar, and when you feed x and y in this order to f, you get this. It so happens that the order here does not matter because of the definition, but in general the order will matter. So this is a very standard definition, and check that f is a bilinear form. It's a simple check, so I leave it to you. Okay, another example. Suppose this is our vector space. It is not very important that we are using real numbers, but just for concreteness, I'm using real numbers in this example. So this is the set of all the polynomials of degree at most n over the field of real numbers, and that is a vector space. We have discussed that earlier. Fix 2 scalars alpha and beta. Then we define this map as f of alpha comma beta, and you feed it 2 polynomials p and q. The output is p alpha times q beta. This is again for all p and q in the vector space. So that's the definition. Again, p alpha is the evaluation of p at alpha, and similarly q beta. So perhaps I should have written a px here, but it's okay. I mean, it's fine. There should be no confusion. And as above, I leave you to check that this is a bilinear form. All right. Another bilinear form. This I won't go into any details because this uses integration, and we are not assuming that the reader is familiar with integrations. So for the reader who knows about integration, this is an exercise. One can just check that this is indeed a bilinear form. All right. So now we will endow the space or the set of all the bilinear forms on a vector space with a vector space structure. So this is itself will form a vector space. So how do we define it? It's all very, very natural. So fix 2 bilinear forms on a vector space V. Then the sum of these 2 bilinear forms is defined as f plus g of u comma v is equal to f u comma v plus g u comma v for all vectors. So just pointwise addition. This is how we add functions in general anyway. So one can check that this, there's nothing to check so far. This is just a definition. Well, yeah, so one has to check that this is a bilinear form. So check that f plus g is also a bilinear form. It's not just some map, it is a bilinear form. Similarly, suppose we have a bilinear form and a scalar. We define alpha f. So one may write alpha dot f if one wants, but this is as of now just a symbol. So this is defined as a map from v cross v to f as alpha f of u comma v is equal to alpha times f of u comma v. Again, this is for all vectors in u and v, and as above, check that this is a bilinear form. So we have addition and multiplication defined on the set of all the bilinear forms, and now I will leave you to check that. Check that this is a vector space over F. Under the above operations, of course. So that is another very simple exercise that I leave you to do. All right, so now something interesting is going to happen. We will identify this vector space with this vector space. So this is the space of all linear maps from V to V star, and this is what we just discussed. It so happens that these two are isomorphic in a very obvious, or rather in a very natural way. Okay, so how do we define? We will explicitly define an isomorphism. Okay, so first we define this map. For f, a bilinear form on the vector space V, we define L sub f as a map from V to V star as LF of u is fu comma blank for all vectors u. Okay, and similarly we define R sub f from V to V star as Rf of V is equal to f blank V for all V in V. And the exercise check that LF and RF are linear maps. Easy exercise. All right. So now define. So in other words, LF and RF are members of HOM VV star. Okay, so now we have a map, or we will define a map from the space of bilinear forms to HOM VV star. We will call this map big theta. And what is this map? This takes F to LF. So that's the definition of theta. Again, check that theta is linear, straightforward. And we will also define, so for a linear map from V to V star, define psi sub t from psi sub t from V cross V to F as psi sub t u comma v is equal to tu applied on v. So what's going on? T is a map from v to v star. So tu is in v star, hence it consumes vectors from v. So this is a functional on the vector space, and you can feed it a vector. So this is legitimate, meaning this thing is indeed something in the base field. So here again, check that psi t is a bilinear form. Okay. So with all these checks in hand, now we can do the real thing. So we have a map. Yeah. So now we have now define capital psi as a map from hom vv star to the space of bilinear forms, which does what? Which takes t to psi sub t, and check that psi is also linear. I hope you're not overwhelmed by this, because it may seem like a lot, but it is not all that heavy. Okay, so with all this in hand, now we can do something very interesting. So we have a map from the space of bilinear forms to hom vv star, and then a map from hom vv star to, again, the space of bilinear forms. This is big theta, and this is capital psi. Okay, so what is this composite? We need to calculate this composite. Perhaps I should do it on a separate page. I don't want to do it in a separate page. Okay, I'll try to do it here. So you start with f, and when you apply capital theta to it, you get LF. And now when you apply psi to it, you get psi sub LF. Okay. So what we want to claim is that this is actually equal to f. So our claim is that psi sub LF equals f. And how do we prove it? So psi sub LF of u comma v is what? This is by definition equal to LF u fed v. Okay, LFU, and then you feed v to it. But this is by definition fu blank, and you feed v to it, because LFU is that guy, which is fu comma v. So on all inputs, f and psi sub LF agree, and therefore these two are equal. So this is equal to f, and hence this is the identity map. So what we see is that the composite of psi with theta is identity. Let me record it here. Psi composed theta is identity. And similarly, this is an exercise. Theta composed psi is also identity. Does that even make sense? 1 second. Yeah. This is identity. So why am I getting confused? Once you apply psi, you reach here, and then you can apply theta to reach there again. So it's fine. So just check this, and maybe, yeah. So maybe I'll take a page. So therefore, thus theta, maybe capital theta and psi are isomorphisms. Therefore, this is isomorphic to this. But the more interesting statement, or more mathematically charged statement, is this one. That the fact that two finite dimensional vector spaces are isomorphic is not saying much. It is just saying that their dimensions are equal. This is saying much more, that there's a very nice identification between them. In some sense, they are the same objects, just different perspective. So yeah, they are isomorphic, and hence in particular, the dimension of the space of all the bilinear forms is equal to the dimension of this space, which we know is the product of these two dimensions. Which is nothing but the square of the dimension of V. So we have figured out what is the dimension of this vector space. In particular, it is finite dimensional, and its dimension is the square of the dimension of V. Okay, so now we are in a position to discuss rank of a bilinear form. So before we define rank, we need to establish something. So fix a bilinear form on V. So then what we have, we have this map, which we just discussed, LF. Right, it's a linear map from V to V star. And dualize this. So apply the dualizing operation. So this gives us a map from V double dual to V dual, and this is the transpose of LF. So all I'm doing is, in general, when you have a map from a vector space V to a vector space W, and it is a linear map, then you get a map from W star to V star, which is the transpose of the original map. So yeah, so dualize this guy, we get this, and now we have this natural identification. We will use the fact that this map, which is V going to phi sub V, which we recalled in the beginning of this lecture, this is an isomorphism. And now what is this composite? So the question is, what is this composite? And we claim that actually this is RF. So claim LF transpose composed with capital phi is equal to RF. Proof is very simple. So LF transpose phi of V is equal to, so basically I'm saying that let little v be an arbitrary element here. You feed it to this map and you show that it is the same, this, we want to show that this is the same as RF of V, so that is the goal. So what is this? This is LF transpose of this guy, which by definition of transpose is equal to phi V composed with LF. Just use the definition of transpose, which is which we want to show is same as RF. So want to show that this is same as RFV, which is to say that phi V LF of X equals RFV x for all x in V. This is what we want to do. But phi V LF of x is, so this is a composite. Phi V LF of x is this, which is f of x blank, which by definition of phi V is this, which is equal to f blank V, and you feed x to it, which is rf V, and you feed x to that. So indeed, we have shown this is the case, and hence this is the case, and hence this equation holds. So we have proven the claim, and therefore, so with the help of the claim, thus, since phi is an isomorphism, we have rank of the transpose of LF is same as rank of RF, which implies rank of LF is same as rank of RF. Right? Because the rank of the transpose of any linear map is same as the rank of the original linear map. So we have this, and this is what we define as the dimension of, this is what we define as the rank of F. So that's a definition. Okay? So we have defined the rank of a bilinear form. Okay, very nice. So let's look at some examples, the examples that we saw. So here are vector spaces Fn, and this was defined in this fashion. So what is the rank of this guy? Basically, we need to find the rank of LF. So if LF of x is 0 for some x, then this is 0, which implies fx ei is 0, where ei is the ith standard basis vector. Recall that the vector space is the coordinate space. So this is the ith standard basis vector, which implies xi is 0. And this is for all I. So this is also for all I, and hence x is 0. Thus, LF is injective, and hence surjective, because V and V star have the same dimension, so it is an isomorphism. Thus, rank of LF, which is by definition the rank of F, is equal to n, meaning the dimension of V. So we have calculated the rank of this guy. What about this person? So I shouldn't say degenerate, is not full rank. So I should have defined degenerate. Maybe I will define it after I cover this example. I mean, it's the same thing as saying that the bilinear form has not full rank, but anyway. So suppose this vector space is in question and alpha and beta are two real numbers, then we want to show that this is not full rank. So f alpha beta of some polynomial is 0 implies, or rather let me say this instead of doing it this way. So let p be a polynomial such that its evaluation at alpha vanishes. For example, something like x minus alpha or x minus alpha square or so on, any such thing. There are other examples, of course, but certainly these do. So if you pick any such thing, then p is non-zero, but this chi is 0, right? So therefore, since so what is this? So this implies that L f alpha beta of p is 0, which means that this guy is sending something non-zero to 0, and hence this cannot be a full rank linear map. In fact, the rank of this is actually 1. And to do this, here is the hint. This is a basis for this vector space. Maybe I should make tuples around it. Yeah, so using this hint, you can show that the rank of f alpha beta is actually 1. Okay, so it is far from full rank. Okay. Now finally we will, so let me define non-degenerate or degenerate. So a bilinear form f on v is called degenerate if rank f is less than the dimension of v. It cannot certainly exceed the dimension of v. At max it can be equal to dimension of v, but if it is strictly less than the dimension of v, we say that f is degenerate. That's just a terminology, and hence all we are saying in this example, not in the proof but in this statement, all we are saying is that this is degenerate and this is non-degenerate. Okay. Finally, restriction of a bilinear form. This is very, very short discussion. So let f be a bilinear form on V, W be a subspace of V, then the map f restricted to W cross W, which is of course a map from W cross W to F, is a bilinear form on W, which we write as, so we write FW instead of so we just abbreviate this a little bit, even though this is the proper way to write it. This can cause confusion, but anyway, this is just a point of notation. So all we are saying is that we have a map from the space of bilinear forms on V to bilinear forms on W. Just send a bilinear form to its restriction. So I'm using this notation instead of that. Anyway, and one can check that this is also a linear map. Okay. So yeah, a lot of things were discussed in this lecture, but I hope you were able to follow. As usual, like, comment, share, subscribe, and I'll see you next time.